Finding the local extrema of a function that is made up of x to some fractional power can be a little bit tricky. And the reason for that is finding the critical numbers by either figuring out where the derivative of your function equals 0 or where it does not exist can be a bit tricky when you're dealing with x raised up to some fractional power. These fractional power functions have a little bit of a unique caveat when it comes to figuring out the domain of the function and by extension, its derivative. So I wanted to show you an example in this video that I did recently in one of my weekly live streams, which I typically do every Monday night at 5 o'clock Pacific time, where I talked about finding local extrema of a fractional power function from start to finish. So I'm going to be going through all the steps of how to do that with this specific type of function, which can be a little bit tricky. So if learning a bit more about that sounds good to you, be sure to stick around to the end of the video. And do keep in mind that the topics I'm going to be going over in this video are all covered in my free Calculus 1 study guide and my complete Calculus 1 package. The links to both of those things are down in the description. But without further ado, let's go ahead and jump into the video and I'll show you what I'm talking about. Find the local maximum and minimum values of this function, b of x equals 3x to the 2/3 minus x. So, like I said in the intro, when you're doing these problems, the first thing you want to do is find the critical numbers. I have covered this in a handful of other videos, especially recently, but just kind of quickly to go over what that looks like, we'll start there. So, first thing you want to do to find critical numbers is you're going to take the derivative of the function. So in this case, the function whose minimum and maximum values we're trying to find is this function here, b of x. We're going to need to take its derivative. So we're going to find b prime of x first. To do that, in this case, we can use the power rule to find the derivative of this first term. So we're going to move our power down in front, multiplying it by our coefficient. 3 times 2/3, the 3's are going to cancel, and we're just going to be left with 2. So 3 times 2/3 is 2. We're going to leave the x as x, and then we're going to minus 1 from the power. Minusing 1 from this is the same as minusing 3 over 3. So you need to have a like denominator when you're subtracting fractions. 2 minus 3 is negative 1. So 2/3 minus 1 is negative 1/3. Okay, so this is going to be the derivative of that term there. Then we have the derivative of minus x. Well, the derivative of x is just 1. So we're just going to get 2x to the negative 1/3 minus 1 is our derivative. So now when you're trying to find critical numbers, what you need to do is figure out where does your derivative equal 0 and where does your derivative not exist. So whatever x values make one of these two things happen is going to be a critical number, which is a spot where we could potentially have a local minimum or local maximum. So we need to basically take this equation, this b prime of x, and set it equal to 0. And then we also need to consider where does 2x to the negative 1/3 minus 1, where does this not exist? I'll come back to that part in a minute. Let's go ahead and start with this, where does it equal 0? So we pretty much just need to take this equation and solve for x. So first we will add 1 to both sides. Then we can divide both sides by 2. Then we can raise both sides up to the negative 3rd power. Because if we raise a power up to a power, we multiply the powers. So we're going to get basically negative 1/3 times negative 3 is just 1. So that just leaves us with x to the 1, which is just x over on the left side of our equation. And then on the right side of our equation, 1/2 to the negative 1/3 would be the same as basically 2 to the 3rd power, which would be the same as 8. So x equals 8 is going to be a critical number that we get from taking our derivative and setting it equal to 0. Now we also need to think about where does this function not exist? Well, there's really only one possible thing that's going to make this function, or this, the derivative of our original function, our b prime of x. There's only one thing that's going to make this potentially not exist. Typically when you're trying to do this, or think about where a function does not exist, what you want to think about is basically what x values are causing you to basically break the rules of math. And what I mean by that is there's certain things that you just can't do, right? You can't divide by 0. You can't take the square root of a negative number. You can't take a log or natural log of 0 or a negative number. So you want to look for those kinds of things and basically figure out what x values would cause you to do one of those, breaking the rules of math things. So in this case, we don't have any square roots, we don't have any logs or natural logs, but we do have a fraction. And it doesn't look super obvious, but what you want to consider is that something raised up to a negative power is the same as 1 over that thing to the positive power. So 2x to the negative 1/3 is the same as 2 over x to the positive 1/3, and then minus 1. So clearly we have a fraction here, 2 divided by x to the 1/3. Basically, if there's any place where this denominator equals 0, that's going to cause us to divide by 0, which is against the rules of math. So we can't do that. So if there are any x values that cause this, that's a potential critical number that we want to consider. And in fact, there is, which would be x equals 0. So you want to be aware of this potentially causing some problems. One thing, let's see here. Okay. So basically, these are the two kind of spots that we want to consider our critical numbers. One thing that you want to kind of keep in mind, though, is going back to our original function. Let's take just a moment and think about what is the domain of this function. The domain of 3x to the 2/3 minus x. Well, there's one kind of issue with this equation, and that is the fact that we have x raised up to a fractional power. Fractional powers are a little bit weird because if you're thinking about specific numbers raised up to a fractional power, right? Like we could take 5 raised up to the negative, or I'm sorry, raised up to the 2/3. We could figure out what that is. Or similarly, we could say -2 raised up to the 2/3, right? We could actually figure out what these numbers are. But in the context of a function, you want to be careful of doing that, because when we have x raised up to the 2/3, if we're trying to think of this as a function, right, we're trying to say x could be any number. This doesn't really work when we have negative x's. When you have a negative number, some number less than 0, when you have a negative number raised up to a fractional power. And the reason for that is kind of the idea of a function is you should be able to basically graph it, obviously, but you should be able to see, if you're thinking about a graph of a function, and let's think about negative x values. I'm just going to sketch an example of a graph. That's not what this looks like, but just in general, let's say you have some function where you're kind of graphing it for x values less than 0, right? Let's say you have something that looks like this. The idea here is that, especially a continuous function, basically x values that you plug into this function and look at, what's the output of that function at that spot. X values that are near each other should give you some sort of result of a y value that's like somewhat in the neighborhood, right? And I mean, it's possible to have like a vertical asymptote, for example, where, going over a little bit in the x direction moves you up a lot in the y direction. But still, there is kind of a continuous path to get there. But when you talk about having a negative number raised up to a fractional power, it kind of creates some issues there in terms of the continuity of it. So you want to be very careful whenever you have a fractional power of your x or whatever your variable is in a function, because basically you're gonna want to ignore negative x values. The function isn't really going to exist for negative x values. So essentially, all that I'm trying to say here is we don't want to consider x values less than 0. We only need to basically go to x equals 0. So the domain of our original function is all x values greater than 0. So just let me clear out some space here real quick. The domain of our original function is x greater than or equal to 0. We don't want to consider negative numbers because we don't want to take a fractional power of a negative number. So as a result of that, that kind of is where our critical number of x equals 0 is coming from, because we don't even really need to worry about what our function is doing for x values less than 0. We only really need to start at 0. So that was a bit of a tangent there, but the point I'm trying to make here is now that we've got our critical numbers, what we need to do is the first derivative test. Well, the first derivative test, how you always want to start that out is just by drawing a number line. So let's just start by drawing a number line. And the only points that you want to put on your number line are your critical numbers. So in this case, we want to put x equals 0, x equals 8. A common mistake that I see people make when they're doing the first derivative test is they will always put 0 on their number line. But you want to be careful with that. You only want to put 0 on your number line if it's a critical number. Or if you have a situation like this, where your function is only defined for x less than 0 or x greater than 0. You don't always put 0 on the number line, only if it comes up as an edge of a domain or as a critical number. In this case, it is the edge of our domain of our original function, and also the edge of the domain of our derivative, because our derivative also has x raised up to a fractional power. We don't want to have negative x's. So once we have drawn our number line, in this case, we have a limited domain. This function and its derivative do not exist for all x values, right? In fact, they don't exist for x less than 0. So we can basically, what I like to do is even just scratch this out, like scribble it out like this, because that makes it obvious we don't actually want to worry about x values to the left of 0. And since our derivative does not even exist at 0, we don't even want to consider x equals 0 either. So basically we're going to start at basically x greater than 0, and we're only going to look at everything to the right of 0. So the first derivative test, what it says is you need to, once you've drawn your number line, you need to pick numbers that are in between each of these endpoints of your number line. So in this case, we've marked off 0 as an edge, and we've marked off 8 as an edge. So we have two kind of sections of our number line remaining here. We have x values between 0 and 8, and then we have x values that are greater than 8. So we have two domains here, x between 0 and 8 and x greater than 8. So again, we don't really want to worry. We don't want to pick these actual points. We don't want to pick 0 or 8. We need to pick some numbers in between them, or greater than our largest one or less than our smallest one. So these are the two kind of intervals that we need to test. What we need to do now is pick some number within each of these intervals. It doesn't matter what number you pick, as long as it is in between those intervals. So in this case, we have 0 to 8. Let's just test x equals 1. It really doesn't matter what you pick. The only reason I said 1 is because that looks like it's going to be pretty easy to plug into your derivative, which is going to be our next step. And I'll get to that in just a second. So we'll say x equals 1 to figure out if this interval is increasing or decreasing. And then we need to pick some x number, which is bigger than 8. Again, doesn't matter what you pick. Just kind of looking ahead a little bit, what we are going to have to do is take the cube root of it. So let's go ahead and pick some cubic number, which the first cubic number bigger than 8 would be 27. So let's say x equals 27. Okay. So then once you've picked your x values, the first derivative test says that we're going to take those x values and we're going to plug it into our derivative. So we're going to plug it into b prime of x equals 2x to the minus 1/3 minus 1. So let me just write our derivative here real quick. So now what we need to do is plug in each of these numbers that we've selected into our function. So we're going to find b prime of 1, and we're going to find b prime of 27. So plugging 1 in, we're going to get 2 times 1 to the negative 1/3, again, is the same as saying 1 over 1 to the positive 1/3. And doing this, 1 to the 1/3 is just basically saying taking the cube root of 1. The cube root of 1 is 1. So 2 over 1 is 2, minus 1 is 1. So it doesn't matter what number you actually get. All that matters is whether this is positive or negative. So in this case, we have positive 1. So b prime of 1 is positive. Okay, so going back up here now to our interval, that tells us since our derivative was positive in this interval, our original function, b of x, is increasing. Okay, you want to always keep in mind the derivative of a function tells you about the original function's slope. So if the derivative is positive, the original function's slope is positive. If the derivative is negative, the original function's slope is negative, which just means that it's decreasing if it's negative, increasing if it's positive. Since b prime of 1 was positive, b of x is increasing at x equals 1. So our function is increasing within this interval. Okay, now we need to find b prime of 27. So that's just going to be, again, 2 over x to the 1/3 is 27 to the 1/3 power minus 1. 27 to the 1/3 power is the same as taking the cube root of 27, which is 3. So this is going to give us 2/3 minus 1. 2/3 minus 1 is negative 1/3. Again, it doesn't matter exactly what number we get, but negative 1/3 is negative. So b prime of 27 is negative. So if the derivative is negative, that means the slope of the original function is negative, which means it's decreasing. So the first derivative test tells us that we have a critical number at 8, which means that it may be either a local minimum or a local maximum. Applying the first derivative test to that confirmed that since it's increasing to the left and decreasing to the right, we have something on our graph that looks like this, which is going to be a local maximum. So we have a local maximum at x equals 8. So x equals 8 is a local maximum. If we wanted to then actually find the maximum value, the local maximum value, we would take x equals 8 and plug it back into our original function up here. So we would just find b of 8 to get our actual maximum, local maximum value there. And I'll leave that for you to do. It's pretty much just plugging it into a calculator from there. So I'll leave that for you. Well, I hope you found that video helpful. If you did, do me a favor and hit that like button down below. It's a huge help to my channel so I can keep making more videos like this. And while you're down there, hit that subscribe button and that bell icon too, because if you found this video helpful, I guarantee you I'm going to have a lot more videos coming out that you will also find helpful. So we can keep crushing it all term long in calculus if you do go ahead and hit that subscribe button. Thanks, and see you next time.